Okay, so we said that if the function output values are increasing, the derivative is positive because we'll have a positive change in y for a change in x. And that will make our ratio, our rate of change ratio, positive. So then right down here. And then if the output values of the function are decreasing, then for a small change in x, we're going to get a negative change in y because the final value of y will be less than the initial value of y for that change in x, making that ratio negative. And so therefore, since the rate of change is negative, our derivative is negative. So this one. So we were looking at this example last time. And so let's just kind of recap. First question is, where's the so f is our accumulation function, the red one is f. And then the blue line is representing the rate of change at the given value of x as x increases, okay? So where is the accumulation, i.e. f of x, decreasing, and how do you know? So I'll give you some key points here, but you go ahead and talk. Where's the accumulation, i.e. f of x, decreasing? So here are the key points. Go. -4. Okay, there should be 15 lively conversations going on right now. Answer question number 1.
Explain why.
So here's some key x values that you might use to define intervals. -4, -1.9, -0.5, 1.1, and 2. What do you think? Where is f, the function f, or the outputs of f, where are they decreasing? In what interval or intervals? How about right here in the gray shirt? What do you think? In what interval or intervals is the outputs of f decreasing?
From -4 to 0.
-4 to 0. How about right here? Do you agree with that? He wants -4 to 0 for where f is decreasing.
I said the interval that I chose was -1.9 to 1.
Okay, we have a new suggestion. -1.9 to, you said 1.1? Okay, so there's two possibilities. -4 to 0-ish, -1.9 to 1.1. What do you think? Or something else? Go ahead.
I think it's decreasing from 0 to 2.
0 to 2, it's decreasing. The accumulation function f. So the red graph is f. The red graph is f. That's our accumulation function, f. And we're asking, where is that decreasing? Yeah.
I'm going to agree with -1.9 to 1.1.
Okay, -1.9 to 1.1. You're saying 0 to 2. So all we're looking at is the red graph. What does it mean for that red graph to be decreasing? It means that for a change in x, the change in y is negative, meaning the final value of y will be less than the initial value of y, or it's going down, right? It's going down. So it's from -1.9 to 1.1. That's the interval where f decreases, or outputs of f. You see it? So I'm just asking, so where does it go down, right? And so you see that in two ways. You see that the function's heading down. How's the other way that you see that f is decreasing? Yeah.
The tangent line shows that it's a negative slope.
We just talked about that. When f is decreasing, then the rate of change is negative. Negative. So in that interval, the tangent line is showing you that the rate of change is negative by the negatively sloped line. Okay. New question. Where's the rate of change of r of x decreasing? And to help you, where's r of x getting less positive or more negative? So where over what interval or intervals is the rate of change r of x decreasing, getting less positive or more negative? Go, talk.
Negative 3.5 to about 0.5.
Saying,
The 7 since the very beginning, it's always
Wait, no more one. No one more. Wait, hold on. More
less
negative.
positive and becomes more negative.
To see more negative.
More 0 to 1. Yeah, it's it kind of tilts. Maybe a little less.
Okay, where does r get less positive? Over what interval does the rate of change get less positive? Yeah.
From about negative 3.5 until approximately negative 1.9.
Okay, so he's saying in this first part of the graph up to the high point, the rate of change is getting less positive. Would you agree with that? Yeah, that's right. And then where is the rate of change getting more negative, which is also decreasing rate of change? What's that? Okay, so it's getting less negative here. Oh, sorry, more negative. So we went less positive or more negative. Where's the rate?
negative 1.9 to negative 0.5.
Yeah, so in this next section, it's like, so the rate of change is decreasing here by getting less positive, and then the rate of change keeps decreasing by getting more negative. So we could say all the way from, I want blue here, -4 all the way to negative 0.5, r of x decreases over that interval. Okay, and so what do you notice about the graph of that tangent line for that interval versus this other interval? Do you see that it's like it's turning clockwise? Do you see that? So it's like for that whole part where the rate is decreasing, getting less positive, more negative, the graph turns clockwise as you move from left to right. And then the rest of the way it turns counterclockwise. So this helps us to say what's true about the function f when r decreases. Well, f in this turns clockwise. CW, clockwise. Okay? And so it makes a shape that we call concave down. Concave down, like a what? Like a frown. Okay? Concave down, like a frown. So when the function turns clockwise, then you have this situation where the rate is decreasing. It's getting less positive or more negative. And then what about over here? So then we have this other, starting at -0.5 over here, f turns counterclockwise. Now it's turning back the other way. And the shape of the graph is concave
up.
Concave up. Like a cup. Like a smile, but cup rhymes with up, so we like that, right? Okay. So So when the rate of change decreases or increases, this is what we can kind of deduce about the graph of f. Okay? So when the rate is negative, we can say that f decreases. But when the rate decreases, we can say that we have concave down shape. All right? Was there a question? Someone had a hand up? Okay, so notice this. We're talking about the rate decreasing. So let's go back to this first thing we did. We have a function. Now it's just the rate function. So if the rate is decreasing, what can you conclude? So we have a rate of change function, r of x. R of x is decreasing. Then what? R of x is just a function, like any other function now. And if r of x is decreasing, then what can you conclude? Derivative of what? The derivative of r is negative, right? So if r of x is decreasing, then its derivative must be negative. Okay? So basically we have, if a function is increasing, the rate of change or derivative of that is positive, and if a function is decreasing, then the rate of change derivative of that is negative. So that's true whether it's an accumulation function or a rate function. That's just because a rate function is just a new function. So it has a derivative, and it follows the same rule as before, as the one we learned before. So now that we're introducing now the rate of change of the derivative. So things start swirling around and getting very confusing. This is what you can hold on to or go back to help you when it gets very confusing with all these relationships. Okay? If you have a function, if it's increasing, its derivative, its rate of change is positive. I don't see anyone writing this down. If you have a function and it's decreasing, then its rate of change is negative. So this is kind of like the bedrock you can hold on to when things start getting confusing, which they always do when you first start practicing this. Okay? So we're gonna so hold on to that. So let's look at now I'm going to show you I've got some function f. R1 is the rate of change of f, the derivative of f. R2 is the rate of change of R1. It's the derivative of R1. Okay? And so right now, x is negative 2.95. And the rate of change of R2 is negative 0.5. And remember, R2 is the rate of change, or the derivative of the rate of change of f. So, what can you conclude? What conclusions can you make with this information right here? So that's what you want to talk about? What do you know? You have the function f, you have its rate of change as R1, and then the derivative of that function is R2, and I'm telling you that R2 is negative 0.5. What can you conclude about R1? What can you conclude about the original function f, if anything? Talk it out. See if you can put this together here. At and
The rate of change of the rate of change.
So R1 is decreasing and the original function
Rate of change.
less negative. No, I mean less positive. Okay, so let's do R1 R2 is decreasing, then R1 is decreasing.
so we have a derivative that's negative. What can we conclude?
R1 is decreasing.
Can we conclude anything about R1? What do you think we can conclude about R1?
If the function is decreasing,
F or R1?
the R1 is decreasing.
He wants we can conclude that R1 is decreasing. Yes or no? Right. If a derivative is negative, then the function of which it's the derivative is decreasing. So we could say R1 is decreasing. Okay? Anything else we can conclude? We've got if R1 is decreasing. Yeah.
Then F is either less positive or more negative.
Well, I think so. So R1 of X would either be getting less positive.
No, I'm talking about F.
All right. So what can we say about F?
It's getting less positive or more negative.
Okay. So you're talking. So what you're saying applies to R1, not F. So if something's decreasing, then that thing is getting less positive or more negative. So it's not F that's getting more positive. So you're just explaining what it means for R1 to be decreasing. That's okay. That's okay. So what could be true about F? Yeah.
It's negative.
F is negative. Agree with that? Lots of nods. So if a derivative is decreasing, then that original function is negative. Is that right? No. If the derivative is negative, then the function is decreasing. But not the other way around. Now you have the derivative is decreasing. We just talked about that on the previous screen. What happens when you have the derivative decreasing, becoming less positive or more negative? So F is? F could be anywhere. F could be at negative 1,000. F could be at a billion. Concave down. That's what we just went over, right? So this is why it's confusing. There's no easy way to learn this at the beginning. Right? The rate is getting, watch the pen, it's getting less positive or more negative. So the graph is turning clockwise, concave down. So you got a negative. The derivative of the rate means the rate is decreasing. If the rate is decreasing, means your original function is turning this way, turning clockwise, concave down. Okay, so that means so we've got something like this, right here at negative. We don't know how high up or down it is. It could be down here, or it could be up here. But we know that it's, we don't even know that. So we know that it's just concave down is all we know. Something like this. Now I'm going to tell you I'm going to show you what R1 is at that moment. Okay. Now I'm going to show you that at that same value of X, negative 2.95, R1 is 1.475. What else can you conclude? Go. What else do you know now? So now I'm just showing you that the rate of change of F is 1.475. So keep going.
F is increasing.
Oh, you determine the function. The function is increasing.
So it's still
So the function is increasing. It's increasing.
Okay, somebody new. What more can we conclude now that I've given you this information that the rate of change at negative 3 is 1.475? Somebody new. There we go. Go ahead.
R1 is increasing at 1.
So the R1 is increasing?
Yeah. Well, it's a new rate, right?
So before we said R1 was decreasing, right? That we have that the rate of R1 is negative, then R1 is decreasing. So does this mean now R1 is increasing?
Yes.
No, R1 is decreasing.
It's becoming less.
We've already decided, we already pinpointed that the first rate is decreasing. All I've shown you now is that rate 1 is positive. Positive 1.475.
Means F is increasing.
Means F is increasing, right? If a rate of change is positive, then its function is increasing. Okay, it goes back to my slide, my screen with the stars on it. So that's what I mean. So you've got all these things flying around. That screen with the equivalencies with the stars is what you can always fall back on. Okay? If a rate of change is positive, if a derivative is positive, then that function is increasing. That means that R1 is positive, f of x is increasing. If R2 is negative, that means its function that it's the rate of, R1, is decreasing. And then consequently then f would be concave down. So what do we have? We have f is increasing concave down at -3. Draw it with your finger in the air. It's increasing, f is increasing. We got that from the first derivative being positive. F is concave down. We got that from the second derivative being negative. So increasing concave down would be just like the left half of what I drew, right? So we don't know how high or up or down it is. I haven't given you any information on what the value of f is. It could be down here, it could be up here, it could be crossing the axis. But we know that from these two values that it's increasing concave down. Okay, I'm going to change n to a different value. First, I'm going to take this off. And let's make n 3.35. Really? Why isn't R2 changing? Okay, well, it's supposed to be changing, but it's also supposed to be negative, so that's fine. I don't know why it's not changing. All right, so I'll make something else up. But it is supposed to be negative. Let's make it negative 8.6. Okay, so here we are at 3.1. Oh, that's really bad. At positive 3.1, and R2 of 3.1 is negative 8.6. Okay, so you're going to start again. What can you conclude, if anything, about R1 and about F? We'll get to that later. Okay. So R2 is negative 8.6. What about R1? And then what about F? Go, talk. Let's just give it all at once here, for time's sake. I don't know why this isn't working. I don't know. It's not working. This is just to be positive now.
If you delete the whole row, you still had a space, and so that's why it wouldn't
Where?
recalculate.
What space?
When you deleted that, you still had that as a blank cell, and so that's why it wouldn't recalculate, I think. It was still trying to do something with, when you like deleted R1 of n, it still had the yellow block there, so it didn't know what to do.
Yeah, but it should be positive now.
Oh, so it's a no.
Oh, no. Okay. No, you're right. Okay, maybe you're right. Let's see. No, because it's still showing negative 0.5. when I have it in here now. Okay, so this is correct though. So now you got R2 negative 8.6, and now R1 is negative 1.55. So what can you conclude about R1 and about F? So what can we say about R1 if R2 is negative 8.6? R1 is decreasing. F is concave down again. Now R1n is negative 1.55. Function F is decreasing. So what do we have? Our original function F is decreasing and concave down at 3.1. Draw it with your finger in there. Concave, yep. So it might look like this. So 3 is off the screen. So it may look like this, or maybe here at 3.1, something like that. Oh, that's why. The wrong function in there. Okay, so does it agree with what we had? Okay, yeah, at negative 3.1, we have increasing concave down because this R2 function was negative and R1 was positive. Here at 3.1, R2 negative and R1 negative, so the function is decreasing because its rate is negative, and it's concave down because the derivative of the rate is negative. So let's summarize. What are we talking about? We're talking all about this, about the rate of change of the rate of change, or the derivative of the derivative. So let's summarize that and talk about some notation here. Okay, so the derivative of the rate of change of x, or the derivative of the derivative. Okay? It's conveniently called the second derivative. So now everything you've done before when you've taken a derivative, you did all those mastery exam problems, that was, now we'll call that the first derivative. So what we just called the derivative before, we're going to specify and qualify as the first derivative. When we take the derivative of that function, it's the second derivative. So these are all notations that you would use to define a second derivative function. All of these mean the same thing. They mean the derivative of the rate of change of f, or the derivative of the derivative. Okay, so here we go. So here's an example. Here's an accumulation function, g, x to the fourth minus 6x cubed plus 12x squared minus 8x plus 3. And we're going to fill in this chart. We're going to find the value of the accumulation, the value of the rate of change, i.e. the first derivative, and the value of the rate of change of the first derivative, i.e. the second derivative, for all of these x values, but we're going to share the load, okay? So you can work with your partner, and you and your partner are each going to pick 2 of these. So either do the first 2 x values, 0 and 0.5, or do the second 2, 1.5 and 1, or do 3 and 2, and find the value of the function g, the accumulation, find the rate of change of g, the derivative of g, and then the rate of change of the rate of change, or the second derivative. So get a partner, work together, and just do 2 of the rows. Pick any that you want, okay? So if your birthday, if your partner's birthday is January to April, do the first 2 rows. If your birthday is May to August, do the second two, and then September to December, do the last two.
I don't care, we're gonna do that. Two numbers.
Choose two rows
What?
and find all these values. Go.
What first two rows? You say you want to divide the quadrant, or you want to, what the hell?
With your partner.
Well, because for me,
I wanna do the number, or you wanna do the okay, just write out what I'm reading. 4x cubed minus 6x squared. Okay, 4x cubed.
Remember, the second derivative is just the derivative of the derivative.
Which derivative? First of all, you have to find the equation because we were looking about it and don't care about it. G of x is that freaking long equation, right? Now write down what is G prime of x. I'm gonna read G prime of x to you. 4x cubed minus 18x squared. 18x squared plus 24x. 24x minus 8. Okay, now second derivative. 4x cubed we're gonna be 12x squared. Yeah, minus 36x plus 24. Okay. Now take out the calculator.
oh, really? I took two. I feel. Well,
Still using your handhelds, huh? How about GC? It's a lot faster with GC. I even also got the laptop. Getting out the laptop. But it's
So much easier though.
just define the function, use function notation. You don't have to punch anything. Right?
Only true if you have a Swift computer.
Oh, okay, that's true too.
You do.
All right, if you want to check here are the first and second derivative. Check your words before you dig a hole for yourself.
Second
Are
derivative.
they like G of X or like G prime of X or G prime of X?
0, 0, 0.
Check your first and second derivative before you
24.
make mistakes.
I don't want to write down.
So you find all.
G prime of 0
So
2 prime. The second derivative. 0.
zero to like
This one is not.
and then plug it in the G sign box and then
Let's say it's negative 8.
second derivative. You find all of them.
So wait, so you use like the original.
I just found the argument right now.
I did there.
Does everybody have at least one row? You've gone across one row.
So
Just so you know what you're doing. Anyone need help creating a row here? 3 values. Everyone good? Okay.
This is the value for G prime of 5.
Row means you're going to find the value of the G function. By the G value of
But shouldn't you have like
precision,
9
value of
numbers
second
then?
derivative.
Not 9, but like
No
6.
calculus involved, right? Evaluating the function. Those. Okay, so you can check your answers. Here we go. See if this is what you got.
Out there.
Check what you've done. See if this is correct.
oh, you're right.
Good? Okay, so now let's talk about what this all means. So let's look at we have the function values. We know that's the total amount of accumulation at that x value. That's the first column. Second column, we want to talk about what does it mean for the function g. So here, -8. What does that tell us about the function g at x equals 0? We have the first derivative is -8. What does it tell us about what's going on at 0? G is what? Decreasing. We have a negative rate of change. And we talked about this. A negative rate or a negative derivative means the original function is decreasing. Decreasing moderately, slowly, quickly?
Relative.
Relatively.
What is relative to how you're speaking?
Okay. Yeah, so for a change in x, y goes down 8 times as much. So for a change in x, this says that y is going to decrease. A small change in x, y is going to decrease 8 times as much as your change in x. Okay? What about we have the first derivative is 0. What does that mean for the original function?
It's not going.
Right, it's staying constant, right? So we call this a pause. So, but it's just at a momentary pause at x equals a half. So I'm going to draw that, but it's kind of a misrepresentation because it's only staying constant for just that one moment of 0.5. When x is 0.5. So we get a momentary pause in the accumulation because the rate of change is 0. What about 1? What does that mean for the accumulation? Increasing, positive. And for every change in x, change in y is the same as the change in x. 1 times the change in x. And then at 2, the rate of change is positive, so the function is increasing. The output's increasing twice as fast as the input. Same thing here, but now the input's increasing 10 times as fast as the input. Okay? And then a 0 again means that momentarily, when x equals 2, the accumulation pauses, doesn't change. So again, this what I'm drawing is all about, we're making deductions about g, right? This is what g is like given those values. Okay? Now, same thing, we're going to look at the second derivative and say, what is g like given these values? So what do we have? We have that the second derivative is 24. What does that mean for g? It means that the rate is increasing, and if the rate is increasing, g is concave up. Turning counterclockwise. The rate's becoming less positive or less negative or more positive. So the graph turns clockwise. Same thing with this. Positive second derivative means an increasing first derivative, which means the graph turns clockwise, concave up. All right, -3 means the rate of change is decreasing, so g is concave down. Okay, so what would a 0 mean for the second derivative? What would 0 mean for the second derivative? It would mean that the rate of change is not changing. So the rate of change is pausing for a moment. So it's kind of like constant rate of change for a moment. Momentary constant rate of change. Or momentary linearity, you can think about it that way. So it's momentarily, the rate of change isn't changing. So you have a momentary linearity. Okay, 24. Rate of change increasing. G is concave up. 0 again. Constant rate of change for a moment. So we're going to put these together, and now let's say sketch of g near x. So what will g look like near x? So decreasing, concave down. Decreasing rapidly, concave down. Look like this. Isn't better. A little more concave. One more try. Get that curve in there. There we go. Okay, and then what do we have? So it's momentarily, the accumulation is not changing, but we have concave up. What would that situation be? So where along here does the accumulation pause or not change? At the low point, right? Right there at the low point, you have a momentary pause. So right there, which is called a local minimum. So right there at x equals 0.5, the accumulation is pausing because the first derivative is 0, but it's concave up because the second derivative is positive. So it's right there at the low point. Both those conditions are met. Okay, then increasing concave down at 1.5. This. Okay. On its way up and momentarily linear, momentarily constant rate of change. Okay, increasing concave up. All right, and then pausing and momentarily linear. Okay, so an example of that might be like this, like x cubed. So right there, the accumulation pauses, and also the rate of change pauses. So the accumulation pauses and the rate of change pauses. So it's momentarily horizontally linear. Okay. All right. Anybody have a question? So you will have homework for Friday. So it'll be posted on